Let's get started. Hello, everyone. I'm Chun Lin from National Taiwan University, and I'm here to talk about our work, which is about virtualizing Arm TrustZone and KVM QEMU architecture and setting up an APT-VM based on our virtualized TrustZone environment. Here is the outline of my presentation. I'll start with a brief introduction to Arm TrustZone and APT. Next, I'll talk about the motivation and the main objectives of our work. And following that, I'll introduce the design of our approach, where I'll dive into the technical details of how we adapted KVM to support our virtualization model. And I'll walk you through the modifications we made to APT to integrate it into our virtualized environment. After that, I'll present the evaluation of our approach. I'll share the execution time of our virtualization model on different APT applications. Finally, I'll discuss some of the future work we are currently planning. Before we dive into the details of our work, let's start with a brief introduction to Arm TrustZone. The key concept of TrustZone is word isolation. TrustZone splits the processor into two distinct worlds, the normal world, where the general applications and operating systems run, and the secure world, which handles sensitive operations like encryption, secure storage, and key management. This isolation between worlds ensures that even if the normal world is compromised, the secure world remains unaffected, providing a robust layer of security. To manage the world switching, TrustZone relies on the secure monitor in ELC. When an application in the normal world needs to interact with a trusted application in the secure world, the CPU will generate a secure monitor code to trap to ELC. Then secure monitor in ELC then performs the world switch to prepare the context for the secure world. Then the CPU can enter the secure world by generate another exception return and enter the secure world and execute the corresponding trusted applications. However, TrustZone only provides hardware isolation. It typically needs a secure operating system running in secure EL1 to provide software management. This secure OS manages the execution of trusted applications and ensures secure operations within the secure world. The most common secure OS is APT, which is the target we try to run on our virtualized TrustZone. APT is a widely used open source framework that provides a trusted execution environment known as T, based on TrustZone, based on Arm TrustZone. One of the key advantages of APT is that it allows developers to implement trusted applications within the secure world. Trusted applications are usually used to handle sensitive operations and are protected from the normal world. And as I previously said, when a CPU needs to switch to a secure world, it generates a SNC to trap to ELC. Then the secure monitor, which is the firmware of APT, then handles the SNC and switches to the secure world. Once the CPU context is switched to the secure world, the APT OS takes over and invokes the appropriate trusted applications. Once the trusted application is executed and complete, the result is passed back to the normal world through the send SNC mechanism, ensuring that the separation between the secure and the normal world is maintained. Now that we have covered the background, let me briefly introduce the motivation and the main objectives of our work. Currently, QEMU TCG supports the emulation of TrustZone, but KVM does not. which means the developer cannot run an AppTVM with the acceleration of KVM. So we had an idea that we could virtualize TrustZone CPU features at KVM and reuse the existing QEMU emulation on TrustZone hardware to create a virtual TrustZone environment for guest virtual machines. So the first goal of our work is to extend KVM to expose a virtual TrustZone to the guest virtual machines. And the second goal is to set up an AppTVM with our modified KVM and QEMU. By doing so, we can demonstrate the ability of our virtualization framework more clearly. Then I'll talk about the design of our approach. The first challenge we met is that guest VM can only execute in EL1 under KVM architecture, which means the instructions which should be executed in ELC are considered as sensitive instructions in our design, including exception return and move with ELC system registers. Those instructions may cause undefined behavior when executed at EL1. Although SNC should be executed at EL1, but it needs ELC system registers to save and restore the CPU context. So we still consider it as a sensitive instruction. And there is a host instruction, often used for semi-hosting code in ARM64. It's also considered as a sensitive instruction, since it may cause the CPU to stop from executing. To manage those sensitive instructions, the most common strategy is to trap and emulate them at KVM. However, not all sensitive instructions would be trapped to KVM. For example, exception return and host instruction may not be trapped. So we adapted a paravirtualization method to replace all of those sensitive instructions in the guest VM with hypervisor code. By doing so, we can force those sensitive instructions to be trapped to EL1 and allowing KVM to handle them. As I previously said, guest VM can only execute in EL1, which means we need to create a virtual ELC environment for those firmware which need to be executed at ELC. This includes creating a set of virtual ELC system registers. So I would like to introduce how we virtualize ELC system registers and how they work. One important observation is that most of the ELC system registers are also banked at EL1, including SPSR, BBAR, STLR, and so on. Which means we can simply virtualize ELC system registers by leveraging the equivalent EL1 system registers. Here's how it works. We simply replace all accesses of ELC registers with their EL1 equivalent registers in guest VM. For example, if the guest VM attempt to access SPSR ELC, we will replace it with SPSR EL1. And here's a simple graph which shows the key concept of our virtual system registers design. As you can see, we multiplex virtual ELC and virtual EL1 system registers onto physical EL1 system registers, which means we create a virtual ELC and a virtual EL1 environment based on physical EL1. And we maintain a virtual system register data at KVM, including EL1 and ELC registers. When the CPU changes the exception level, we need to put the correct virtual registers onto the hardware. For example, if the CPU makes an exception return to go back to EL1, KVM will save the virtual ELC registers and then restore the virtual EL1 registers onto the hardware EL1 to ensure the system state is correctly saved and restored. In addition to the registers that exist at both EO1 and EO3, there are a few registers that only exist at EO3. These registers, such as SCR EO3 and NDCR EO3, play a crucial role in managing the security state and debug configurations of the system. Currently, because these registers have no direct equivalent registers in EO1, our design cannot multiplex it on the hardware. So instead, accesses to these EO3 exclusive registers are replaced with hypervisor code. And KVM can keep tracking the state of these registers, which means the guest VM can also update and check the state of these registers in KVM. But the state of these registers will not affect the real hardware. Another key challenge in our approach is emulating sensitive instructions like secure mind code and exception return, which may cause the changes of exception level. So next, I'll introduce how these two instructions are emulated in our approach. Let's start with the emulation of SNC. When the SNC instruction is trapped to KVM, we first set the current program counter to the virtual EOR EO3. This ensures that we can return to the correct address when the exception handling is complete. Next, we set the current process state to the virtual SPSR EO3. This includes saving important information like condition flags and processor mode, so that we can correctly restore the system state after the exception handling. After that, we set the current program counter to the virtual VBAR EO3 with the corresponding offset. This step redirects execution to the EO3 exception vector table, allowing the system to handle the SNC as though it were operating in EO3. And finally, as I previously said, we need to perform a context switch to save and restore virtual system registers. In SNC, KVM saves the current virtual EO1 registers and then restore the virtual EO3 registers onto the hardware EO1. By following these steps, we can accurately emulating the behavior of an SNC in our virtualized TrustZone environment. Then it comes to how we virtualize exception return. The handling of E-rate in our implementation follows a similar approach to that of SNC, which just simply restores the state set by SNC. First, we restore the program counter from the virtual EOR EO3, and then we restore the process state from the virtual SPSR EO3. They were both set by KVM during the emulation of SNC. Finally, we can perform another context switch, but this time we save the current virtual EO3 registers and restore the virtual EO1 registers onto the hardware EO1. And also, to support our virtualized TrustZone environment, we made several key modifications to QEMU, particularly for emulating the secure memory and handling I/O operation. First, we added a virtual secure memory region within QEMU to emulate the secure memory used by TrustZone. Within this secure memory region, we also mapped secure peripherals such as UART and general purpose I/O. By configuring secure UART, we are enabled to set up the console of the secure world of ART. Another important aspect of our QEMU modifications is how we handle semi-housing codes. Semi-housing allows a program running on an emulated system to communicate with the host environment, typically used for debugging and I/O operations. Semi-housing code in ARM64 is triggered by host instruction, which is considered as a sensitive instruction in our approach. So same as exception return, we need to replace them with hypervisor code first. Once the semi-housing code is trapped to KVM, we return the control from KVM back to QEMU to allow QEMU to take over and handle the semi-housing request. In QEMU, we leverage the existing Arm TCG semi-housing handler. This means we didn't modify the semi-housing handler, we directly utilize the TCG semi-hosting mechanism to handle those semi-hosting calls. By incorporating these modifications into QEMU, we have created a more realistic emulation environment for TrustZone. Next, I'll introduce the paravirtualization detail of ARM. Most modification we made to ARM is about the untrusted firmware, which is the firmware of ARM. It is responsible for the boot process for ARM, including initializing the hardware, managing the security features, and loading the ARM OS into the secure world. In addition to managing the boot process, untrusted firmware is also responsible for handling SNC for ARM and thus managing context switching between the secure world and the normal world. Untrusted firmware consists of several bootloaders, each playing a different role in ensuring the secure initialization and operation of the system. The first stage of the boot process, bootloader 1, is responsible for initializing the early hardware components and setting up some critical security features. Normally, bootloader 1 should be executed at EL3. So in our design, we need to replace all the instructions which will access EL3 registers with its EL1 equivalent. After the initial setup, bootloader 1 will execute an EWRITE and go back to secure EL1. Then bootloader 2 takes over to load and verify subsequent bootloaders and system software. Since in our architecture, bootloader 2 will run in EL1, we don't need to do many modifications to bootloader 2. Bootloader 3.1 is the core of untrusted firmware. It is a runtime firmware responsible for handling SNC and managing context switching between the secure and the normal worlds. Since bootloader 3.1 also runs at EL3, same as bootloader 1, we need to replace all the instructions which will access EL3 registers with its EL1 equivalent. And the next stage is bootloader 3.2, which will load and initialize the RPOS in secure EL1. Since bootloader 3.2 runs at EL1, no specific modifications need to be done here. Finally, bootloader 3.3, which is U-boot in our context, is responsible for loading and initializing the normal world OS, usually Linux. And as the same as bootloader 2 and bootloader 3.2, no specific modifications need to be done here. Yes. After all the modifications we made to ARM, we successfully set up an ARM VM on our virtualized TrustZone with QEMU KVM. So next, I can present the performance evaluation of our implementation, and here is the environment setup. The evaluations are performed on AVA developer platform with Arm Neoverse N1 CPU. The Linux version of our modified KVM is 5.15, and the ARM version is 4.0.0. To evaluate the performance of our implementation, we measure the execution time of 7 different trusted applications in an ARM VM. These applications are provided by ARM in the ARM examples repository. The first 2 trusted applications, ACipher and AES, can help us evaluate the cryptography performance in our virtualized TrustZone. And Hello World, it is just a simple application which can serve as a baseline to measure the transition time between the secure and the normal world. And secure storage, it helps us to evaluate the performance of secure data storage operations. And the last one, plugins. This application interacts with the Linux system log service as a plugin. It helps us understand the ability which the secure world can call a Linux service, can call a normal world service as a plugin. And here are the results of our evaluation. We additionally evaluate on QEMU TCG with the stand-up-T version for comparison with our KVM approach. In both environments, we evaluate the execution time of 7 trusted applications I just mentioned. And as you can see, in most applications, our virtualized TrustZone on KVM is about 10 times faster than TCG. Except for the plugins application, since this application invokes Linux system log service, we believe that our operation dominates the performance. So the execution time of it didn't show a significant difference between KVM and TCG. And at the end of my presentation, I'd like to talk about the future plan of our work. First, we aim to extend our approach to KVM-based confidential VM, which means we want to leverage existing confidential VM like pKVM or unconfidential compute architecture to provide strong memory isolation and protection to our approach. In addition, currently QEMU hardware abstraction only supports a few TrustZone-based devices. So we plan to extend QEMU to virtualize more secure I/O devices. For example, we currently aim to virtualize the TrustZone address space controller. The TZPC can define memory regions that can be accessed by the secure world while preventing unauthorized access from the normal world. By virtualizing the TZPC in QEMU, we can better emulate secure memory access and improve the memory protection from the to the secure world. This is the end of my presentation. If you want to contact me, here are my linking and email. I am welcome for any further discussions. Thank you for your participation and any questions.
So you mentioned you had to change a number of the instructions to paravirtualize. I was a little unclear how you were doing that. Are you building a special version of trusted firmware on OptE, or are you patching it live as it runs?
We changed on a specific version of Arm trusted firmware. We didn't patch while it runs. We didn't do a runtime patch.
So it's a compile time change to build that version. You've made a fork and patched that manually.
Yes.
Right. Okay. Thanks.
Hi. Yeah. Thanks for the presentation. So there's one thing that I think is might be a little bit fragile with I think when you were talking about replacing EL3 register accesses with the EL1 equivalent, I think that'll work in some cases, but as far as I'm aware, in a number of cases, the registers aren't quite the same between those. So for example, you might have bits in the EL1 register or the other way around, which are reader 0, write ignore. And I'd be a bit worried that if you remap that access, you might lose some of the state, or worse, it might have an unintended side effect. So I think you might be better off using hypercalls for the registers as well, just so you avoid having to debug that, because it would be very difficult to figure it out.
It depends on different registers. Some registers in EL1 and EL3 have different structure. Maybe in EL3 it's a 32-bit, and in EL1 it's a 64-bit. So we check it in KVM while KVM prepare the exception level context switching between EL1 and EL3. We do a transformation between the correct structure for EL1 and EL3 registers.
Right, I'm just saying that the CPU might not offer all the storage that you need, so you could lose bits in some cases.
Oh, yes. Yes.
Thank you for the presentation. I have a question that is not for you, but it's more from the people that know the inside of Arm EL3 design. What is the reason why the hypervisor cannot optionally trap SMC and ERET, if you know?
It's supported. It's not in the base architecture, but it's supported. You got it with nested and with FGT as well. Have you considered? Have you gotten to the point where you've modeled security states in the GIC? Because it also applies to system IP as well, and the GIC is an example of something in KVM where you might need it.
Currently, we didn't consider the security state in EL3. Yes.
Did you consider at some point to run the TrustZone firmware in EL0 instead, so that you wouldn't have to modify it because you would be able to trap everything, including current EL, instead of doing binary modification?
I'm sorry, did you mean that we didn't?
So you could run the trusted firmware, basically what was at EL3, run it at EL0 instead. And all your privileged registers will be trapped.
Yes.
Including the current and exception level. Do you think that would be realistic, or the performance impact is too big?
Oh, I don't know that exception return could be trapped if we didn't replace it.
So for instructions that undef at EL0, you actually can take that to EL1, and if you could run like a little bit of shim code perhaps at EL1, then you can figure out how to route it from there and emulate the instruction. And then you could do your hypercalls from the EL1 shim that you're running into KVM or. Yeah.
Yes, you're right.
When you context switch from the secure and insecure world, do you have to change the page tables as well, or do they have the same view of memory?
Yes, the page table is maintained by the RTOS itself, and we just need to, or the RTOS will change the page table based registers.
I mean the stage 2 page tables, because they might have a different set of.
Stage 2 page table,
I guess my question is, like, I would expect when you do a context switch, you need to flush all TLBs because the page table may be different at stage 2.
Yes,
I don't know
we
if
will
you
flush the
have
TLB, but we didn't do stage 2 page table switch.
So slightly related question. Normally from the secure side, you are able to get a non-secure mapping. So you can, from the secure side, access non-secure memory. I was curious how you made that work.
And in our current implementation, we didn't do a lot at memory protection. Our work is just simply a proof of concept that we could virtualize TrustZone CPU features. Yes, so as I previously said, in our future work, we may extend our approach to some of existing confidential VM to which that they can provide memory protection to our approach. So, thanks for your participation.